Let's prove an even more interesting claim about graphs. So let's let G be a graph where every vertex has degree less than or equal to k. Then the claim is that G is k plus 1 colorable. So again, G is a graph. It could have many vertices. We're not saying anything about how many vertices it has, but we are saying that every vertex has degree less than or equal to k. And in that case, we're saying that G is k plus 1 colorable. So by the way, a graph where each vertex has degree less than or equal to k, we would say that the max degree of G is less than or equal to k. The proof is by induction. That's why we've been doing all these proofs by induction. Now, in all of our previous proofs by induction, it's been pretty obvious or pretty simple to write down what the induction hypothesis to be, what your predicate should be. In this case, if we do the obvious thing, it won't work. And that's what's really interesting. So let me show you why the obvious approach for writing down the predicate doesn't work here. So what would you do? Here's how you would start a proof by induction. You would say P of k is just what I've written above. Any graph G with max degree at most k is k plus 1 colorable. Okay, that's how you would start to write your predicate. Seems reasonable. I myself would try and do it this way. Okay, and then let's try P of 0. That could be our base case. P of 0 is any graph with max degree less than or equal to 0 is 1 colorable. That means you're given a graph, all of the degrees are 0, and you want to show it's 1 colorable. Well, if your graph has degree 0 on every vertex, it means your graph just looks like this. There are no edges at all. And so yes, it's 1 colorable. You can assign just 1 color to every one of these vertices, and it will be 1 colorable because there are no edges. So the base case is not a problem. Now we need to show that for all k, P of k implies P of k plus 1. Okay. Let me move this up so you can see P of k. So we assume P of k is true. We need to prove P of k plus 1 is true. So what is P of k plus 1? It says any graph G with max degree less than or equal to k plus 1 is k plus 2 colorable. Okay, so let G have max degree k plus 1, need to show it is k plus 2 colorable. My step 3 would be, since G has max degree k plus 1, then there has to be a vertex with degree k plus 1. So let V be a vertex of degree k plus 1. Okay, like I said, G has max degree k plus 1. We have to show it's k plus 2 colorable, so let's let V be a vertex of degree k plus 1. That's a valid step. Then I'm going to remove V from G and all of its edges. A slightly odd step, but it's common when you're doing induction on graphs. You take your graph, you take your vertex v, you remove it, and you remove all the edges that connect v to g. We're left with g prime. And when you're left with g prime, what you'd like to do is to apply the inductive hypothesis to g prime. You'd like to say, okay, I've removed v from g. Now I have this graph g prime. Its maximum degree has gone down because I've removed v from it, and so now I can apply the inductive hypothesis to g prime. The problem is that even though you've removed v from g, there could be many vertices that have degree k plus 1. So just because you've removed one vertex from g doesn't mean that you've decreased the degree, the maximum degree in g prime. I mean, if I have two vertices in g that have degree 10, and I remove one of them, g prime still has degree 10. So the inductive hypothesis, which talks only about graphs that have max degree k, it doesn't necessarily apply to g prime because the maximum degree hasn't necessarily gone down. And so we can't directly apply the inductive hypothesis to g prime. So let me show you how a proper proof of this would go. Let's recall what we're trying to prove. So G is a graph where every vertex has degree less than or equal to k. We want to show it's k plus 1 colorable. Again, it's a proof by induction, but this time I'm going to do an induction on n, the number of vertices, as opposed to last time where we did induction on the degree. So I'm going to write this as follows. Any graph G with n vertices is max degree of G plus 1 colorables. What does this say? It says that give me any graph with n vertices. You can always color it with max degree of G plus 1 colors. Okay? So notice it's different. Last time we were doing induction on k, the degree. This time I'm doing induction on n, the number of vertices. And this is what we want to prove. We want to show that for any graph with n vertices, you look at its maximum degree, you add 1, and its max degree of G plus 1 colorable. Okay, just move this up. So the base case, I'm going to leave to you. It's very simple. And then we need to prove that for all n, P of n implies P of n plus 1. What does this mean? Well, we're allowed to use as a fact that any graph with n vertices is max degree G plus 1 colorable. And we need to prove that any graph with n plus 1 vertices is max degree G plus 1 colorable, where G has n plus 1 vertices. So it's like you're given this graph with n plus 1 vertices, and you can use this fact that if you had given me a graph with n vertices, you could color it as follows, as a subroutine. Okay, so you have this subroutine, you can color graphs with n vertices. You want to know, given an arbitrary graph on n plus 1 vertices, how can I color it? Okay, so step 1, remember we need to prove Pn plus 1. Pn plus 1 is any graph G with n plus 1 vertices is max degree G plus 1 colorable. This is Pn plus 1. And we get to assume Pn is true. So let G be a graph with n plus 1 vertices. Let V be a vertex in G. Then what we're going to do is interesting. We're going to remove V from G, and we'll obtain the graph G prime. So we had G, it had n plus 1 vertices. We took some vertex V, an arbitrary one, we ripped it out and all of its edges, and we got G prime. Now, P of n tells us that G prime is max degree of G prime plus 1 colorable. Right? That's the power of the inductive hypothesis. We know P of n is true. Since G prime has n vertices, we know that it's max degree G prime plus 1 colorable. We know that's true. Okay. In the worst case, max degree of G prime plus 1 equals max degree of G plus 1. Right? I mean, in the absolute worst case, you need just as many colors to color G prime as you do G. I mean, think about G prime. You took out a vertex from G prime. So G prime, you need less than or equal to as many colors, however many colors you needed to color G. Well, certainly you need at most that many to color G prime. Maybe G prime requires even fewer colors than G because you've taken out a vertex. But in the worst case, the number of colors that you need for G prime is equal to the maximum degree of G plus 1. Okay, maybe you ripped out a vertex, but you still need just as many colors to color G prime. Fine. So we've colored G prime using max degree G plus 1, which we'll call max degree G plus 1 colors. We've colored G prime. Need to color G. How do we finish our coloring of G? Well, so we need to put back V and color V. Right? Move this up. Remember, the only difference between G and G prime is that we took out this vertex V. Let's do there. Okay, so we need to put back V and color it. Well, let's look at V. This is the one we removed. How many neighbors does V have? V has 8. V has at most max degree of G neighbors. Right, so V has at most max degree of G neighbors. So again, in the worst case, all of these neighbors have different colors. So remember, this guy is colored in G prime. It's colored in G prime, it's colored in G prime, it's colored in G prime, it's colored in G prime. We've already colored it, all of the neighbors by induction. What if they each have different neighbors? Then we need to use a new color to color V. Okay, but how many colors do we have to play with? Well, we said that G prime, in the worst case, required max degree of G plus 1 colors. So we're seeing potentially max degree of G colors in its neighbors. That leaves one color left over to color V. So I guess step 9 is even if all of V's neighbors have different colors, there's still a leftover color for V. Okay, so again, we used induction to get a coloring for G prime that required max degree of G plus 1 colors, we noticed that that's enough colors for me to recolor V, so we've colored, this completes the coloring of G. Let me go through the proof just one more time. The high-level idea is we're given a subroutine to color a graph on n vertices. We want to color one on n plus 1 vertices. So we're going to take a graph on n plus 1 vertices, rip out a vertex, color the remaining subgraph on n vertices using induction, and then put that vertex back in, and we have enough colors to recolor that one vertex that we had ripped out. And so that will complete the proof. So G is your graph with n plus 1 vertices. We picked any vertex V and G, we removed it, we got G prime. The inductive hypothesis P of n tells us that it's max degree of G prime plus 1 colorable. In the worst case, the inductive hypothesis gives us a max degree of G plus 1 coloring. We've colored G prime, we just need to color G, so we need to put back V in and color V. So here's a picture of V. V has at most max degree of G neighbors, so that's max degree of G colors surrounding V. That means there's one color left to color V and use only max degree of G plus 1 colors. So even if all of V's neighbors have different colors, there's still a color left over for V, and the total number of colors is still at most max degree of G plus 1, because you had at most max degree of G neighbors and you got to use one extra color to color V. Again, I encourage you, if this was slightly confusing, to rewind the video and watch the development again.